Well, good morning, everybody. So my name is Zhonglu. I'm from Southern Methodist University. On behalf of my co-authors, Dr. Fei-Fei Qu and Dr. Jingwu Kim. All right. I thought it didn't make it right. Thank you. So Dr. Jingwu Kim, we are from Southern Methodist University in Dallas, Texas, and as well as my co-author, Dr. Mike Turgo from Harris-Galveston Subsystem District. So we are going to report to you what we have done in the past few years to look at the deformation over the Gulf Coast. Of course, I think, so what I'm going to tell you a little bit the background, motivation, and we are very familiar with this subsidence. So this is the Gulf Coast is no exception. So show you our study area from all the West Texas to a little bit northern Florida, because many work has been done by my colleagues in Florida, so I try to avoid the southern part of Florida. But like any part of the Earth, the Gulf Coast is deforming. At any moment in time, this place is deforming, right? So Earth's tide or whatever, atmosphere tide. But what I'm going to talk about really is the human-induced deformation. So this long-term, the groundwater pumping and the salt dome and the minings and as well the hydrocarbon extractions and the oil gas activities really make this the Gulf Coast very unstable. So it's here to show you the locations of our salt domes, and also the oil field is very, very, very enormous dense. So of course this instability has already produced enormous damage, and many of you probably know, but I do. That is, of course, the wetlands are being lost because of the inundation of the water and the subsidence. And you'll see more frequent the floodings because of subsidence, of course, the fault infrastructure damage as well. We have seen through. So hopefully you are already very good, know the basic of the InSAR processing after this keynote speak by Shaman. So we're going to tell you that we process all the data from ALOS-1 and a little bit ALOS-2 and Sanudo data over the whole Gulf Coast. So using time series analysis using our supercomputers, which is free to all the faculties in either our universities. So we done basically is the time series analysis and including both the persistent scatter InSAR as well as the distributed scatter InSAR. And we try to address two things. One is the precision. So how we do precision? We look at the overlapping area between two tracks and try to see the uncertainty between the disturbance, between two tracks. And we try to do the accuracy assessment using the continuous GPS measurements. So this is to show you the average deformation map we produce over the Gulf Coast. So this is from the ALOS-1 data from 2007 to 2011. It is we look at the data over the overlapping tracks, right? The data overlap by 10 kilometers approximately over the ALOS-1 data over this area, and we address that the precision is about 10 millimeter per year. So comparing with GPS data, we see about 10 millimeter per year as well. So we identify numerous subsidence zones. So how I count it is a very arbitrary. So we lay out some, let's say, well, the subsidence cone, if it's larger than 1 kilometer, and in dimension, we name it the subsidence cone. We also identify numerous uplift. So this is show the very dynamic deformation over the Gulf Coast. So here we process data over the Gulf Coast using Sentinel-1 data from 2016 to 2019, but over the Houston, we process up to the present. Here, because of the time, very frequent time acquisition, almost 12 days, 24 days, so we pin down actually precision reached to about less than 5 millimeters, and accuracy is about 5 millimeters per year by comparing the InSAR deformation with the GPS measurements. So we also see the more transient details because of time, frequent time acquisition from Sentinel-1 data. So this is a very, very critical part for InSAR. Comparing our InSAR measurement with GPS data, GPS are courtesy by the Nevada Geodetic Network, as well as Dr. Bob Wang from Houston Night, that he operated Houston Night. So we compare this here, show you a few examples of the GPS InSAR comparisons, right? And see that this is how we derive about 9 millimeter per year to 4 millimeter per year with for our ALOS-1 measurements and the Sentinel-1 measurements. Now, I'm going to show you some typical representative deformation features. It's not comprehensive. If you want to look at them all, the paper just come out from remote sensing environment about a couple weeks ago. So number one, of course, we know we get groundwater induced deformation. This is the Gulf Coast have numerous subsidence cones caused by groundwater subsidence. This here show you the one of the examples. You probably here is over the Houston area. Here we also not only show you the ALOS1 data and the Sentinel-1 data, but also show you the ERS1 and the MVSAT and the Cosmos schematic data. So the substance, of course, you can see we use a very similar color bar here showing the deformation spatial extent. The rate decrease as function of time, change spatially, moving from to the northwest. So here showing from 5 centimeters per year in about 1990, that time period to about less than 2 centimeters per year to the current stage. Of course, I think if we compare this one with groundwater level change, there is a very nice correlation showing many deformation probably that's related with groundwater withdrawal that is reached to about 0.8 correlation coefficient. So this is also, I think, if you have listened to a talk by Mike, that is really demonstrate the success of Harris Gulf Subsidence District, that the policy they implemented try to manage the use of groundwater to reduce the subsidence. So for Houston, because we have enormous ground-based data, we compare the observations, including ALOS1, Sentinel-1, as well ERS1 data with some GPS observation, right? We show the agreements, and see here how we show you the precision we can reach to 10 millimeters per year to 4 millimeters per year. But over one locations, we show you is very beautiful. I love it. It's my favorite over this one location. The GPS is anchored to about 600 some meters. And here we show the long-term extensometer measurements, and see our InSAR measurements agree well with the extensometer measurements. But you can see that this GPS measurements didn't present a lot of deformation because most water actually is harvested at a shallow location, and GPS is below shallow location. Of course, though, this GPS showing more and more deformation as a function of time. But comparing with the GPS and the extensometers, you can see extensometer measurement is much higher. So again, combining InSAR and other measurements to allow us to characterize the water extractions. Another example also happened at the Beaumont port in Texas. I'm sorry, didn't show up very nicely here. And see this long-term deformation, groundwater extraction over here, and particularly over this municipal airport, and see the subsidence actually can be reached to quite a 4-5 centimeters per year. Of course, decrease the function of time. Here we show at a few locations, we also compare the InSAR measurement with our GPS measurements and show you the ALOS2 and Sentinel-1 data. The beautiful part is the subsidence decrease as a function of time. The second category we call it the subsidence due to hydrocarbon extractions. Of course, the oil gas are produced in Texas. So here we show the deformation over the different several locations in Texas, and also this is Louisiana to show the deformation. So the deformation here is very beautifully showing that is we identify many substance features due to the oil gas activity. And the substance actually centered over the oil field and conformed within the boundary of the production domain, and also correlate in a time-wise with the production activities. So we show when we compare the time series deformation with production. Of course, I think this is we see more this kind of substance features over the Sentinel-1 period. Some of the substance actually is very localized, right? So here is going to here, so very localized, and some of the here and there. So over one of the very nice one of the North Dayton salt domes, and we look at the ALOS1 data. And from 2 different tracks, and we see actually this is not easy to detect because there's many ground surface disturbance. But we see kind of like an overall substance pattern, and over these places, so actually we do see a little bit of uplift. So we were very puzzled by what's the uplift. Turn out when we look at the production histories, that is showing this area actually is the gas is being injected into this salt dome area was a natural storage. So that's why we see the localized uplift. So it's very small, 1 centimeter a year. So again, time series observation and the multiple observation from different geometry allow us to confirm the observations. Due to hydrocarbon activities, we also see here in the corpus Christi, this has long-term substance in history, particularly in the from 1940 to 1975, and the substance continues in recent years and decreases as a function of time. And in another locations here, and we see this is the in this counties in Texas, we see these numerous subsidence cones, and we also see some moving and decrease as a function of time. So the third category is substance due to the salt mining, and the salt mining here is one of the example shown here is the 5 islands. This is the salt dome over the South Louisiana. This is the salt dome. As you can see, this is numerous wells. All the black dots are the wells, and we see the substance over the mining. So some of the mining are done by the ruler and pillar activity, some of the solution mining, and we found the ruler pillar production way produce more substance than the salt mining. So here we see deformation from different time and different observations confirm our observations. So the third category is now we move to the uplift. The many uplift happened in here. So hydrocarbon productivity, there's a byproduct wastewater. So we are going to deal with the water. We want to inject into deep aquifer to let our mother nature to help us to clean up the wastewater. So here we see numerous of these cones. Just give you a mosaic. So this is happen normally about 1 to 2 kilometers about in dimension, and normally centered around the injection well. And the pond is a few centimeters for uplift, sometimes last decade. So substance is hazards. Uplift also similarly will be another type of hazards. So in our we did a very detailed fully covered polylastic model to understand the processes of the deformation, because here we have the injection rate and very localized that allow us to see a lot of stuff that we are currently doing on. So due to the wastewater injections here, we show you a few examples, and a few show different time period from the 2007, 2011, 2015, 2018. You can see this is the very beautiful uplift. We can show by time series analysis, show this average deformation rate. Then, because we know the well locations and all the injection volume are being reported, so we compare the injection volume and show on this is the gray scale here, and then we compare also the inflations. You can see the inflation actually is pretty much correlated with the injection, and in these particular cases, you see this is the variation. So you can see the injection volume going up. You can see the deformation. We only have data from here to here, right? And then we don't have any data. We have no idea. But you can imagine the inflation will continue to move on. So this stop injection here, we still before the couple months before the injection, we see the injection, and the soon injection stops, and you see here deflations, substance, basically diffusion. Purely, this is the hydraulic examples to see how this, if you stop injection for this aquifer system, basically diffuse away. So of course, such ground instability will do something on the faults, right? We can using the InSAR discontinuities to look at the faults. Here we show you the example of a Houston area where we show the mapped faults comparing with this yellow line, comparing with the white dots. That is the faults mapped by the LiDAR data, which you'll probably take $1 million in order to get the LiDAR, the fault over here. But we see here, we can see many of the faults that identified in LiDAR data using the InSAR measurements. And in some locations, I can show you here, this yellow line, right? This is not shown in the LiDAR data, but you can show in the InSAR as well. So of course, InSAR shows the active movements, and the LiDAR shows the long-term accumulation of this particular faulting activity. So the time-wise can be different. So we also we model some of the faults, and we see the faults basically all the faults are striking about along the Gulf Coast, dipping to the southeast to the Gulf Coast to the sea, and to model the fault movement over this area is not tricky, actually. So, but we found that normally the slope is distributed about a couple, 2-3 kilometers. So how that the slope will affect long-term seismic hazards and future earthquakes, that's something remain to be seen. So we compare our data over here and with some other the ground-based measurements here, and we can see very nice correlation between identified faults and here. So finally, the numerous infrastructures are being in place there. So we see how this InSAR data can be used to assist the infrastructure monitoring. Here, show you over the Houston area, we are some of the water pipeline being produced. We see that this over these routes, what's the current deformation rate based on Sentinel-1 data. So see the current deformation of some location here, moving the profile from here to here, so range to about a couple of centimeters can be reached, which should that be risk concern? I think it's better to know than we know nothing about it. So because the oil gas activities, the Gulf Coast is underlined by, laced by numerous dense subsurface pipelines used to transport the gas and the fluids. So this is the subsurface pipeline, right? So you can see how which of the pipeline can be damaged, can be endangered by the surface deformation. And you can lay out the deformation with the highways, and here show you with the highway you probably want to do repair in the future, right? So now we look at these sinkholes. This sinkhole is published by the levees over the Louisiana. We have the levee bridge during the Katrina in 2005, and this is one of the largest flooding events in the Louisiana, in the New Orleans area. And we saw actually from 2007 to 2011, this New Orleans area is very, very stable. I mean, less than a few millimeters of subsidence. But what you see here is very beautiful, this levee. This levee was breached in the Katrina, and then you can see this during 2007. You see about subsiding by about 4 or 5 centimeters a year. Some people must notice, some people must report. When you look at Sentinel-1 data, there's no deformation. So some of the buildings deformation, you add numerous building deformation here. They show you this is the background images, high-resolution photos show the different years, and we see the deformation over the clusters of different buildings. So the point is beautifully poroelastic deformation. The loading caused by the building loading can last for decades. So you can see this for up to from few million per year to. So I think conclude, you can see, hopefully I show you the human-induced deformation is the #1 issues in the Gulf Coast. And we can look at, we produce for the first time the average deformation rate. Of course, this is now is can be easily done over the whole Europe, over the Norway, and the United States is going to have this upper product. We are going to have this product in about a couple of years over the whole North America. So we identify this deformation and the zones. This will allow us to do some further analysis by combining physics-based model, pretty much and using the injection and extraction volume to understand not only the deformation phenomena, but also characterize the geological properties based on deformation. So this is our ongoing work, and this is the paper published, and this is some of the work we published based on also this area. Thank you for your attention.
Thank Mr. Q's presentation. And any questions for Mr. Q?
Thank you. What an amazing data set. I mean, this is really cool. I had 2 questions. One, when you have these localized pumping or injection, like over the oil and gas fields, there's often a lot of horizontal displacements, and I was curious if you looked at that. And the other was, I thought I heard you say you're looking at the all of North America. Did I hear that right? Or
yeah, that will be done by Opera.
Okay, so you're processing over the
GPL
whole
product. Yes.
Wow. Okay.
That will be available in about by the end of next year. We are also part of that product as well. So David Becker is leading that product. Is funded by NASA.
The ARIA.
Based on the ARIA.
Okay.
Yes.
Okay.
So the first one, yes, we do see is a very, very, you know, I'm trying to understand this process, right? So I'm not hydrogeologist, but I'm fascinated by the process. So the injection and the extractions is really based on is how much the rate you're going to do here. If you want to do slowly, if everybody can incorporate things here. So it's not a simple processes, but for the, you are looking at hydraulic activity in the West Texas, we do see that often allowed. So to look at the deformation, we need to know how much it injected, right? So we normally use the CO2 to do hydraulic fracking or do the water do the hydraulic fracking. So we have to look at the night between the extractions and injections, but we often see some deformation as well. So the hydraulic fracturing, actually, in some cases, we can see the fracturing in the West Texas due to the fracking activities.
Thanks. And you saw horizontal as well as vertical along some of those localized areas?
Yeah, I mean, yes, all the deformation is we see the long side motion. So there's always a 20-30% of horizontal deformation compared with the vertical one. So 20-30% come from the horizontal. So the three-dimensional continuum Earth material. So we see the primary vertical, but do have horizontal deformation. But what I want you to see, you'll see the hydraulic fracking for the even though the horizontal moving, right? So we still see the pressure change in such a kind of like the domain. So we still see the most vertical deformation instead of horizontal one.
Interesting. Thank you.